Hi there, this is Jacob Nash Engineering Lessons, and this is Unit 2.1, Lesson 7 on Statics and Free Body Diagrams, Standard 2.1.3. Now there will be 3 videos on Standard 2.1.3, which is basically just the basics of statics and free body diagrams. And then lessons 10 and 11 are going to be on standard 2.1.4. I'm not sure if there will be more than 11, but as you can see, this is a big unit. Um, that's and I apologize that I haven't posted in a few days because I did lesson 6 on centroids, but haven't done a video since then, and that was like the beginning of December. Well, it still is pretty much the beginning of December anyways, but let's get started. Always happens. For some reason, the arrow keys don't work sometimes. Statics introduction. So, statics, that's what this unit is called, if you noticed. So, statics is everything that we've discussed so far. But this is a branch of mechanics concerned with the bodies at rest and forces in equilibrium. This applies in civil engineering because you need to understand what forces are on the object so you can make sure things don't collapse. Because an example that PLTW uses is there was a Hyatt hotel in Kansas that collapsed in like 1981, and that killed over 100 people, unfortunately. And it was because of poor statics understanding. So that's why it's important. And then a rigid body is just a solid body in which the deformation is zero or so small that it can be neglected. Basically, this means that it's going to remain the same size and shape no matter what the force. So you can put on 1 Newton or 1 million Newtons, and it has such a small or non-existent deformation that nothing's going to happen to it. Then mechanics is a branch of physics that deals with the motion of objects at a large scale. So Newton's 3 laws, you've probably heard of this before, and these are 3 laws that Isaac Newton formulated after figuring out physics. And here are 3 videos that are examples of these 3 laws that I recorded. So it's a video within a video. So law 1 is an object at rest stays at rest unless acted upon by another force. So it's a very short clips, but hopefully you'll be able to hear. But I basically just say the same thing that it says above. So an object stays at rest unless acted upon by another force. So that's kind of pointless if you think about it. I mean, like, not the law, obviously. The law isn't pointless. The video, because all I do is just like push a plastic golf ball around. But that really is an example. That golf ball stayed at rest until it was hit by another force, which was my hand. Then law 2, this one is typically the hardest to understand for some people, but I explain it. So the acceleration of an object is proportional to the net force acting upon the object and inversely proportional to the object's mass. So really, in simple terms, this just means that it's just explaining the relationship between the force, F, M, mass, and A, acceleration. So the force equals mass times acceleration. So in other words, the smaller the mass, the smaller force needed. So see this video for an example. The smaller the mass, the less force needed. So, hopefully you could tell that was a golf ball and a baseball, and the golf ball was plastic and small and light, and since it had a smaller mass, smaller force was needed to get it to go and accelerate, but the baseball needed more force. Then law 3 is for every action there is equal but opposite reaction. Well, this can be used as like a metaphor also, obviously, because like if you think about it in like political terms, like if some political group does something, there's going to be a reaction from the other one that's opposite. But in physics terms, you can see this video. For every action, there's an equal but opposite reaction. So, at first, you might think, how is that an example of it? Well, the golf club hit the golf ball. That was a force. But there was also an opposite force. Now, I wish I could kind of draw this out. I probably should have done that. But believe it or not, the golf ball itself also released a force. So it was opposite. So it released a force on to the golf club. A better example, maybe to understand, is a boxer punching a punching bag. They have a force by punching it, but the bag is going to come back. And it comes back because it's the equal opposite force. Because it like, well, technically it could be just because you made it go up and gravity would bring it back down because of what it's hanging on. Like that's a tension force. We'll talk about that more later. But there is a actual like kind of invisible force that comes back from the punching bag. Like if a basketball player is doing a slam dunk, when their feet hit the floor after jumping, the floor actually like has a force that goes up that matches the force that came down. So that's what Newton's third law means. Oh, that wasn't supposed to happen. Sorry about that. It's trying to play the videos. Okay. Equilibrium. This is a fancy word for just saying the state of balance. So nothing's happening. So basically, that ties back to the first law where we said an object stays at rest. When it's at rest, it's in equilibrium. So, taking that into consideration, let's answer these questions. So, which situation, A or B, is in equilibrium? Think about it. The arrows show how much force there's going to be. It would be B, because if you see, there is 30 newtons of force this way, and there's 27 this way. So there's a higher force, so that means it's going to go this way. It's not balanced. These are unequal forces. These are equal forces, that's why. Then what would be the result of each situation? For situation A, it would go 3 newtons to the right. How do we get that? 30 minus 27. Because if you think about it, if 30 goes this way and 27 goes this way, the 27 from the 30 cancels out with this 27, which makes this 0 and this 3. So it will go 3 newtons to the right. For B, it will, since it's in equilibrium, it will go no newtons either way. So it just cancels out. Types of equilibrium. Static. There is no net force acting upon a particle or rigid body. This means there's no force at all. So 0 newtons both ways. It's an equilibrium. Translational. There's no unbalanced forces. So there are forces, but they're not unbalanced. That's the same thing as on this slide. And then rotational. The sum of clockwise moments equals the sum of all the counterclockwise moments. Oh, sorry, I accidentally took out my mouse chip. About a pivot point. So it's kind of hard to, I meant to do a picture for that one, but if you think about it, kind of like, I think what PLPW does, they have like a sort of like lever-shaped thing, and the moments, basically the forces that go around, are going to equal the clockwise ones and the counterclockwise ones. So therefore, the sum of Fx would equal 0, Fy would equal 0, and the sum of m would also equal 0. So units of force. What do we do to describe force? So There are two ones that you can do, and it's LBF, which means pounds of force. I meant to say pounds with a S. Um, and then N for newtons. So here's a map showing what countries use what. Of course, in the United States, where I am, if you're watching this from the United States, we're one of the oddballs. The only other country, according to this map, that you oh wait, there's one there too. Sorry. Um, so this is Thailand, and unfortunately, I'm not the best with African geography. That may be um uh Ghana. I don't know. I'm sorry. I can't. That's not the point, though. This isn't geography. This is engineering. But these three countries are the only ones they use newtons only or newtons and pounds of force. So um, we use pounds of force. Remember, we use that in the thermodynamics unit. But or we also used it when we were talking about beams. Also, I'm pretty sure. But in this case, we use newtons, and I guess the non-existent people that live in Antarctica use it too. Um, Free body diagrams is the last thing. So these are a graphical model of the forces acted upon a specific object. So in the next lesson, I'll talk about this more, but these books are stacked. Let's say they're books. What forces are on them? For all of them, they have the same forces. So they have a force going up, which is called a normal force. I'll talk about that, and then a gravity force that brings them down. Now, they're in equilibrium because they're not moving. That's why there's two forces. If there was only a gravity force, then they would just be falling down forever. But there is something that they're sitting on. They're sitting on each other and on a surface. And a surface always exerts um, a normal force, what's called a normal force. And that goes back to the Newton's third law because there's a not non existent, but non visible, invisible force that acts up, that matches that's coming down, which is the gravity force. Thanks for watching. See lesson 8 for forces, more about forces, what I just talked about. That was very brief. And see lesson 9 for activity 2.1.3. If you're watching this as soon as it comes out, they're not going to be there yet. But that's probably unlikely since I get no views. As of now, at least. So thank you for watching, and that'll be it.